Appreciate you showing up. I noticed you lower the blinds. I assume that's to keep the, suppress the tendency to look out the window and wish you were playing Frisbee or something. It's a beautiful day, and thanks for showing up. I'd like to start off by seeing if the effect will actually work with this audience. So I want you to look at this stimulus, the one that's labeled standard. I'm going to show you for 10 seconds 4 options that represent either the same stimulus, the standard, from a different point of view, or something different. And your job is to tell me which is the one that's right. So I'm going to give you 10 seconds. Ready? Go.
Three.
Raise your hands if you think it's number 1. Number 2. Don't be chicken, come on. Number 2. Number 3. Number 4. Who said number 1? It didn't work. Number 1 is the right one. Numbers 2, 3, and 4 are mirror images of the standard. Number 1 is the standard rotated, seen from a different viewpoint. Like I said, numbers 2, 3, and 4 are the mirror image of the standard. So if we had obtained the effect, then a higher proportion of men than women would have said number 1, and for numbers 2, 3, and 4, presumably a higher proportion of women would have. But maybe I didn't do it right. The news that was made by this 1971 paper by Shepard and Metzler in the journal Science was that mental rotation could be used to investigate certain chronometric properties of mental imagery, by which the authors meant the time it takes to rotate mentally, if there is such a mechanism at work, the time it takes to rotate an image mentally is proportional to the degree through which it has to be rotated. The mental image itself has to be rotated. So these graphs on the right show this operation, this chronometric operation. So you can see that the greater the degree of rotation, the longer it takes subjects to rotate the objects, the object pairs. And it doesn't matter if the angle of rotation is in the picture plane or in sort of 3D depth. It works both ways. That's picture plane, and this is 3D depth. So 2 interesting facts about mental rotation is one is the implications it might have for mental imagery, for our understanding of mental imagery. For example, is mental imagery, if there is such a thing, is it better described as analog or is it better described as propositional? That is, propositional being symbolic. I don't really know what the answer is, and I'm not sure anybody really knows what the answer is. I'm not going to talk about that. What I'm going to talk about today is sex differences in spatial skills, in particular sex differences in mental rotation. So a number of different tasks have been used to assess sex differences in spatial skills. Here's just a small example. There's dozens of different tasks, but here's just a sample. Spatial perception, here we have the water level task, and your job is to say, of the 4 options, what would a glass look like if it had water or some other liquid in it, and it would be tilted. And the correct answer here is 1, but surprisingly, it seems pretty trivial to me, but surprisingly, a lot of people pick 4. I've already described the mental rotation task. Embedded figures task, your job is to find, or to tell me whether or not in these sort of more complex figures, whether these simpler figures are embedded. And the answer is, for all 3 of these choices, the answer is yes. Here's a paper folding task, another example of a spatial task that's been used to examine sex differences. So you take a piece of paper, you fold it in half, and you fold up a corner, and then you poke a hole in it and you unfold it, and your job is to tell, sorry, you don't fold it in half in this particular example, you just fold up a corner, poke a hole, then you unfold it, and your job is to tell me which one it would look like, and the answer in this case is, what is it? 8. Yeah, it's 8, thank you. Okay. No, they're not meant to be equal difficulty. There's just different ways of assessing spatial perception. So the interesting thing about these different tasks is they don't always lead to sex differences, but if you do the task better than I did in the introduction to the talk, by and large you will get sex differences in a lot of different cases. So here's a couple of tables from two papers that were, in one case a meta-analysis, in another case a review paper of sex differences in spatial skills. So I'm just going to sort of highlight the relevant portions of these tables. So if you look at just the effect sizes, these are effect sizes for sex differences in these different tasks. I'll just zero right in on it. Spatial perception, spatial visualization, and mental rotation. You can see the effect sizes are rather large, or reliable in some cases, but substantially larger for mental rotation than for other kinds of spatial perception tasks, larger than for spatial perception, sort of paper folding and water level, things like that, in spatial visualization. So mental rotation really seems to bring up the sex differences. Here's that meta-analysis I was describing, Boyer et al., 1995. The largest effect size here was for a mental rotations test, larger than these other tests of spatial abilities. Okay, so there seems to be something special about mental rotation and bringing out sex differences. So, a very interesting question, I think, is the developmental origins of spatial perception. So if you look at this table, again, I'll just sort of zero in on the relevant stuff. If you look at this table from that review paper I described a minute ago, and if you just look at these different age groups, under 13, 13 to 18, and over 18, you can see that with age comes larger effect sizes. Such that under 13, you might predict that there really wouldn't be any differences in performance between boys and girls. Here's another table, or a graph I should say, from that paper. Again, a lot of studies being summarized here, but if you just look at the effect sizes here on the y-axis and age is shown here on the x-axis, large effect sizes for children and adults older than about college age. When you get down here into adolescence, the younger you go, by and large, the more absent the effect sizes become in terms of sex differences in spatial skill. To test the hypothesis that the sex differences in spatial skills emerge with age, Levine et al. Did the following task. Your job is to tell me what these two things would look like if they were to be put together. Different ways of presenting it, only one at a time. These things are shown to children. And the correct answer here, I believe, is this thing. It's the only way that it can come together. So here is a table. I'll show you the difference between boys and girls, and I've cleverly highlighted them as blue and pink, not to be sexist. So if you just look at the different ages here, here's boys, performance of boys, and performance of girls. The older you go, here's about 6.5-year-olds, 6-year-olds, etc., down to about 4-year-olds. The older kids do seem to show a difference. The younger kids don't seem to show a difference. So starting at about 4.5, 5 years of age, the differences in performance, sex differences in performance, seem to come out. So this seems to imply that there is a developmental phenomenon at work here. There's obviously a lot of controversy about sex differences in many kinds of cognitive skill, including spatial perception. But it's much more broad than this. You might remember a few years ago, I don't really want to bring this all up, it doesn't really matter. Remember the Harvard president, Larry Summers and all that sort of thing? Flurry of activity among the Harvard faculty, including Elizabeth Spelke, who wrote the following article, arguing very strenuously against any sort of intrinsic sex differences in aptitude for mathematics and science. And part of that article, she talked about evidence from infants. So this is worth reading, I think. Thousands of studies of human infants conducted over 3 decades provide no evidence for a male advantage in perceiving, learning, or reasoning about objects, their motions, or mechanical interactions. Instead, male and female infants perceive and learn about objects in highly convergent ways. And this conclusion accords well with that of McAbee and Jacqueline, whose review in older literature led them to characterize the notion that girls are more socially oriented and boys are more object-oriented as the first of many unfounded beliefs about sex differences. So really laying down the law there. So we really do see some evidence from what I've presented that for children anyway, young children, there don't seem to be sex differences in spatial skills. And here's a sort of a theoretical reason to confirm that in infants. But I think it's worth questioning whether or not we can just accept that at face value. We have seen robust sex differences in older populations, in particular mental rotation. I've already described that. We also know from a small literature, but an interesting and important one, I think, that there are organizing effects of hormones on spatial performance. So here's a task that is sort of child-friendly, was given to young children, preschoolers and early elementary school age children, in which your job is to tell me if this is the same teddy bear or not, the teddy bear with his hand raised up, and the answer is yes in this case, even though it's rotated. So in this particular study, they had access to the prenatal hormone levels of testosterone for these children. And what's plotted here is the basically success at this particular mental rotation task plotted on the y-axis, and the degree of the amount of prenatal testosterone that was available to the fetuses, I suppose you could say. Girls are shown here on the left and boys on the right. They're non-overlapping amounts of testosterone, because boys prenatally have a lot more testosterone available than do girls because they produce it themselves, produce more of it, I should say. So if you look at the girls, there's a very strong, reliable correlation, such that the higher the level of prenatal testosterone available to the girl fetuses, the superior, the better their performance as children on this mental rotation task. This study is a little bit problematic, though, because it shows a negative correlation on the boys, and that was really unexplained in this paper. But still, it's interesting to think about. There's another literature on what's known as congenital adrenal hyperplasia, which I don't really want to get into very much because, frankly, I don't understand it all that much. I'm not an endocrinologist, but it has to do with a problem with the adrenal gland, and it's producing too much androgens. When this happens in boys, there are not a lot of functional consequences. When it happens for girls, the consequence, well, there are functional consequences, but they're more easily dealt with for boys. But for girls, the consequences can be more devastating because the androgens are fighting with the female hormones, such that when the babies are born, they're often unclear as to which sex they are. You have to do DNA tests in some instances. So they're an interesting case study in thinking about organizing effects of hormones. So let's talk about CAH-affected individuals in a second. In this particular study, which came out in 1986, males and females in affected families, the affected families of CAH individuals, were tested for differences, sex differences in performance on different spatial perception tasks. And in all cases, males outperformed females. That's shown here in this top graph. And the bottom graph shows differences between CAH and control females and CAH males and control males. Males, by and large, are not affected by the condition CAH, but CAH females dramatically outperform their controlled females to which they're compared in all instances except one of the tasks, the paper foam board task. I'm not actually sure what that is. But by and large, CAH seems to spur an advantage in spatial abilities in these affected females. So there is something special, according to this study anyway, about androgens and organizing this particular cognitive skill. Now, this is controversial. Here's an example of a study that failed to replicate that effect, showing, these are adults now, showing CAH females and their overperformance or lack of overperformance relative to different controls. CAH females did not differ relative to their controls, and in fact, the males somewhat outperformed their male controls, and the researchers are not really sure why that is. So this effect is not completely replicable across populations, but still, there is a suggestion that there is a role of hormones on organizing spatial performance. Now, another literature tells us that infants are sex-typed from birth, so here the question is, how differently are male and female infants treated? So there's a whole, and you probably can't even see this very well, but there's a whole range of adjectives that new parents were asked to use to describe their infants. And these are brand new babies, still in the hospital when these questionnaires are handed out to the new parents. So if you just look at some of these, large featured versus fine featured, strong versus weak, hardy versus delicate, feminine versus masculine, there are reliable differences in how parents describe boys versus girls from the very start. So it's difficult to know how you can determine if a baby who is just born is large featured or fine featured, other than sort of some pre-existing tendency on the part of parents to think about their babies in particular ways. Strong, weak, hardy, delicate, good eater, poor eater, how do they know that? Sociable, non-sociable, alert, inattentive. Almost all these things lead to attributions of sex differences. So we think this really tells us that infants are sex type from birth. There's a very small literature on this next phenomenon, but you may know about this study. Adult monkeys in, are these in Georgia?
No, these are here. These are the Sepulveda.
Ah, okay. So you know this study better than I do, obviously. So adult monkeys are given toys, and the question is, do the adult females and the adult males have different sort of preferences for, these are human children's toys. And here's a couple of examples from this paper by Alexander and Hines, Jerry and Alexander and Wilson Hines. It seems that males and females, male adult monkeys and female adult monkeys, seem to treat or interact with masculine human children's toys differently, such that the male monkeys prefer masculine toys more than do female adults, and the female adults seem to prefer feminine toys more than do the male adult monkeys. Not so much, no sex differences in the neutral toys. There may be the same kind of an effect in human infants. This is a very, very simple study using an eye tracker showing infants aged about 7 months. Just different toys, dolls, represented by dolls here, sort of girly type toys, and boy type toys, dolls versus trucks. Boys don't seem to show much of a preference, but girls seem to look longer, just as measured by fixations reported by the eye tracker. Girls seem to look longer at the dolls than the trucks. So maybe even in human infants, I didn't really want to talk about the Baron-Cohen results, but I guess we could if you want to, because I'm just not sure about those studies, so I didn't want to talk about that. So, all these studies seem to raise very interesting questions and seem to suggest that despite the strong reasons to think that boys and girls don't treat objects differently, it seemed to us that we could investigate mental rotation more directly by employing specialized methods. So that's what we did. So here's a study that we did in my lab, and we set out to look at mental rotation using those sort of nonsense cube figures that I showed you at the very beginning of the talk. So what we did is we used a visual habituation method with infants, showed this stimulus to babies until habituation of looking occurred, and habituation just means decline in looking across trials. So the way it works is you sit a baby down, baby's sitting in the dark, there's nothing else to look at except this stimulus on the screen, and you let the baby look as long as he or she wants. And they look, and then they look away, and then you show it again, and then they look, and then they look away, and you show it again. And you show it until looking declines according to a predetermined criterion, which is something like half the looking across trials relative to the first couple of trials, first 4 trials in this case. Okay, so after habituation, which we think reflects a sort of underlying process of boredom and learning about the stimulus that you're showing, we show 2 test displays, and these are shown after habituation. And each one is designed to match in some way what the babies might be learning about the habituation stimulus, but in fact one is the same object seen from a different point of view, and the other is its mirror image. So the idea is, if a baby recognizes the sort of 3-dimensional configuration of the habituation object, then let's see, which one is the right one? It's this one, right? So this one should be more familiar, relatively more familiar, the one on the top. And the one on the bottom, because it's a little bit more different, it's actually a mirror image, should be perceived as more novel and thus recruit more visual attention. Okay, so we're looking for a novelty preference for the thing that's more different relative to the habituation stimulus. Okay, make sense? Okay, it's a very, very common method in studies of visual perception and cognition. So here are some results. So we tested 5-month-olds. I'll tell you about some other data in a minute from younger kids. We tested 5-month-olds, and you can see there's a novelty preference, a statistically significant novelty preference for male 5-month-old babies, but not female 5-month-old babies. So we think that means that, in this particular age group anyway, under the conditions that we provided, the males recognized the equivalence of the habituation and test stimuli that were the same orientation in space, but seen from different viewpoints, rotating through different orientations. Discriminated them from the mirror image and showed a novelty preference for the mirror image. Yeah.
Since you were showing us the effect sizes before, what's the effect size here?
I don't know off the top of my head.
Okay.
Yeah, I don't know. Yeah, I can look that up for you, or calculate it for you. It's okay. Okay, all right. We tested younger infants as well. We tested 3-month-olds under exactly the same conditions. And here we got a familiarity preference. So this is a bit of a headache for those of us who do infant studies, because people who don't do infant studies look at this and start throwing things at us because they go, how can you possibly come to any firm conclusions about infants making discriminations if you don't really know if they should be making novelty preferences or familiarity preferences? And my response to that is, please don't throw it. Well, you can if you want, I'll just try to duck. But my response to that is, yes, it's true that most of the time you do get novelty preferences as an index of discrimination, but familiarity preferences are really not that difficult to understand. Younger infants, in general, this is really pretty intuitive actually, younger infants need more time to process complicated visual stimuli. For example, a sort of strange, unfamiliar object rotating in 3-dimensional space. And even after a period of visual habituation, they might still need more time to process, in which case they might show a familiarity preference. And that conclusion is backed up by pretty substantial literature. So we think that the 3-month-olds are showing the effect, I mean, there's a reliable preference anyway for the familiar as to the males, but the females don't show any evidence of discrimination. Our conclusions were confirmed using a slightly different method by Paul Quinn and Lynn Libben, who, it was a very interesting coincidence. We submitted this to Psych Science last year, and we didn't know about their study. They submitted it in the same week that we submitted ours, and the editor accepted them at the same time, and they were actually published back to back, which was kind of interesting. And the reviewers said, one of the reviewers who actually reviewed both papers said, this is great, but it should be replicated. And so our studies started to replicate each other. So it was a nice little coincidence. Anyway, what Quinn and Libben did was sort of conceptually similar, but they used a visual preference paradigm in which the numeral 1 was shown in different orientations, side by side, and then the same orientation of 1 and its mirror image were shown in the novel orientation. And the babies look longer at the novel orientation. I should say the boy babies look longer at the novel orientation. So this is just a series of familiarization trials. Here's the test trial. Boys look longer at the new orientation. Girls showed no preference. That's shown over here. Boys showed about a 63% preference for the new one. Girls about a 50-50% preference. These were 3- and 4-month-olds. So really kind of in between the ages that I just described.
So the boys here had a preference for
The boys here had a preference for the novel. Yeah. So our boys had a preference for the novel and the familiar. These boys had a preference for the novel.
This is 2-dimensional, right? Your
Yeah.
study is 3-dimensional.
Right. That's right. Okay, so one other set of studies I wanted to talk about, looking at infant sort of visual cognition. This is a phenomenon we've called 3D object completion. So we use an habituation paradigm that I described earlier. Here, the object is sort of this thing that you would assume is like a wedge sort of rotating around a 15 degrees around the vertical axis. After babies are habituated to this, they're shown 2 test displays, and you're familiar with that method by now. And the question here is not whether, well, that's pretty surprising, isn't it? So the question is if they perceive this as complete in 3-dimensional space. That's what we call 3D object completion. So if the babies assume this is a solid 3-dimensional object, then this lower stimulus should be sort of familiar, and this sort of hollow thing should be novel. Both the from very limited vantage points, both of these stimuli are consistent with what was seen during habituation, but only this one is consistent with an expectation of 3D solidity. So here's the results from that study. We tested 4 and 6-month-olds, we tested 9-month-olds as well, but they acted like 6-month-olds because 6-month-olds can already do it. I'm not talking about sex differences here, but I'll get to that in a second. 4-month-olds didn't seem to have much of a sense of 3D object completion, and 6-month-olds did, and that evidence comes from the fact that they look reliably longer at the hollow display versus the complete. Okay? So we thought, that's interesting. What would happen if we tried different kinds of stimuli? So we tried this L stimulus, which we reasoned would add a bit of complexity to the task for the babies. It's a more complex object than that wedge. It has more vertices and more sides. But we used exactly the same method, habituation followed by 2 test displays, and there's a hollow L and a solid L. Okay, so same method, but with a more complex object. So here's the results from that study. If you look at the 4-month-olds, no difference in looking at the hollow versus the complete among the 4-month-olds for males or females. For the 6-month-olds, males showed the effect, looking longer at the hollow stimulus after habituation to that sort of rocking L. And 9-month-olds, both males and females showed the effect. So I think what we're seeing here is a sex difference, but we're seeing the development of through infancy, we're seeing the infants develop faster when they're males at this particular version of mental rotation, if you want to think about it that way. Males seem to develop faster than do females. Okay, so just to sort of summarize for now, we see sex differences in mental rotation in adults and children, and now from our studies from my lab and from the Quinn and Libben study, we now have evidence, I think pretty good evidence, that we can look for evidence of mental rotation in infants as well. So now we come to the part of the talk that is a little less, what's the word, a little more speculative. So I'll tell you about some ongoing ideas that we've been working with. We don't really know what the developmental mechanisms are, but as a developmental psychologist, that's principally what I'm interested in. I've talked about in this talk the organizing effect of hormones, prenatal hormones as well as possibly postnatal hormones. There could be downstream effects of any intrinsic preferences that could exist, intrinsic preferences for some kinds of stimuli versus others, and I'll get into that in a few more minutes. And I've also talked about differential treatment of infants and the different experiences of infants that they may bring on themselves through these intrinsic preferences. So we really have 2 kind of current working hypotheses. One is that MR is something that's real, and the other is MR is something that really kind of isn't real. So it could be that MR, mental rotation, it really is a valid index of sex differences in spatial skills. On the other hand, it could be that as tested, this effect really is an artifact of other kinds of sex differences. So one possibility is if we measured testosterone in the infants as they came into the lab, it could be that the infants who have a higher concentration of testosterone at that particular time on that particular day could be the ones who outperform the others. And so this could be true of boys, it could be true of girls as well. There could be, certainly I would expect there to be differences in testosterone levels in girls, and it could be that the girls who just have sort of naturally occurring higher levels of testosterone outperform the other girls. This is testosterone, by the way. So we have a couple of grant, I wonder if anybody in this room is reviewing the grant applications. I don't know. Give it a good review if you are, please. So one way in which we propose to do this is by sticking a little cotton swab in the baby's mouth and measuring testosterone in saliva. You stick it in this little test tube thing and send it off to Pennsylvania where the Salometrics company is, and they'll measure the testosterone in the baby's spit. And then we can see what the babies did on that particular day and see if those things line up. So you may know about these studies that look at the ratio of the length of the the second and the fourth digits, which is shown here in the past 5 presidents, and you can see that there are differences among these different hands. And this supposedly is a marker for testosterone in the blood. Do you know about these studies? Yeah, so we could do that actually pretty easily in the lab. We could just slap the baby's hand down and take a picture of it. And I thought about doing that, I just haven't done it because a friend of mine whose name is Sherry Berenbaum, who's done a lot of work on CAH, she says this is a bunch of hooey. So I'm not saying it's a bunch of hooey, so I don't know if it's hooey or not. If not, yeah, I don't know. If you're interested in getting your thoughts, think I should be doing this?
Dan Fessler has an opinion on that.
Yeah. He told me at the beginning of the talk not to take any questions except clarification questions, so should we stick to that? We have time. I mean, I'm going to be done talking pretty soon, so I'm really happy to be interrupted. If you have an opinion on this, please continue. Okay, maybe we can come back to that. Anyway, that's something if we get the money, we will be doing this, and we could be doing this. I don't know why we shouldn't be doing it, because it's so easy to slap a kid's hand down and take a picture of it. It's so easy. But we haven't done it yet. So that's one possibility, is different ways of looking at testosterone, individual differences in testosterone, and see if that maps onto mental rotation performance. Another idea we're sort of batting around the lab right now is maybe there is a male advantage for different kinds of stimuli and a female advantage for, say, social stimuli. And we're really not quite sure what to call the male advantage. Could it be for abstract stimuli or mechanical stimuli? I'm sure there's a range of opinion in this room about what that might be. So one way in which we're investigating that is with a study that is being done in collaboration with some folks here in this room. Willem Frankenhaus and Bailey House and Clark Barrett. This is a very simple study of infant preferences, and I'll set this, this is a movie I'm going to set in motion in just a second, in which we're asking the babies, well, we're asking them to just tell us which one they prefer of a choice of two side-by-side presentations of two dots that move independently, but on one side of the display, they're designed to actually interact in a manner that is consistent to adults with chasing. So I'm going to set this in motion. This is an attention getter we show between trials to recenter the gaze. This little blue dot is the baby's point of gaze. This study is done on an eye tracker, so we just show these displays one after another. It's as simple as that, and we just let the babies look and we record their eye movements. So I'll just set it in motion here. It makes noise, you can't really hear it, but it doesn't matter. So what do we got here? The one on the left is the chasing, yeah? The other one's very boring. I'm glad to report you're as smart as a baby.
So now they flip sides. So now chasing on the right, the child moves to the right.
Right, so all of that is, randomized and everything, of course. So this is a good example of a baby who seems to prefer the chasing to the random display on the left, in this case, in which the objects don't interact. But this is a good example, but it's not atypical at all. I'll show you some data in a second. All right, so you get the idea. So here's some data. We have lots of data, actually. I'm just going to show you the results from the first experiment. The proportion of looking at the animate or the chasing motion that you just saw. Differences between boys and girls. Boys are shown as blue and girls are shown as green. We tested 4-month-olds and 10-month-olds. Chance level performance is 50%. That's shown here as this dotted line. So first thing I wanted to point out is if you just look at all four groups, boys, girls, at 4 and 10 months respectively, all the groups are above chance, reliably above chance. Second thing to notice is for the girls, they're way above chance, and there doesn't seem to be a difference in their preference as a function of age. The 4-month-olds and the 10-month-olds seem to prefer the animate or the chasing display about equally. Boys, however, show a stronger preference at 4 months than they do at 10 months. So they're still preferring the animate motion at 10 months, the chasing motion, but it's reliably reduced relative to the 4-month-olds. So we think what might be going on here, again, sort of a working hypothesis. We have lots of other data, but it's relevant to the work on MR because it might be reflecting a shift in preference on the part of boys with age when they're young infants a shift in preference away from sort of socially oriented stimuli toward more abstract stimuli. Yeah, so we don't really have very firm conclusions at this point, but we're actively sort of pursuing that hypothesis and others. Another way we're pursuing this hypothesis is with a study in which we're testing mental rotation, but now we're testing mental rotation of hands. So if girls have a sort of advantage for social stimuli, we might actually expect to see the sex difference go away. The sex difference we saw for the novel stimulus after habituation to a rotating stimulus. I'll just set this in motion now, so this is what it looks like. It rotates through 240 degrees, like that cube stimulus I showed you earlier in the talk. But it's a hand, it's a computer-generated hand. So after habituation to the stimulus, the babies see the same hand, and that's, I believe, shown at the top. Yeah, okay. This is the same hand, but seen from a different point of view, and that's the mirror image of the other hand. In this case, it would be the right hand down here. So again, the question is, after habituation to this hand, do babies show a novelty preference for the new orientation, the mirror image? And the answer is not so much. So we're really kind of scratching our heads about this one, or I should say I am, because I only got the data on Friday, and I've been struggling over the weekend to come up with a nice story to tell you. And I have one on the next slide, but this is not it. We're not seeing sex differences in mental rotation in 3-month-olds, or in this case 6-month-olds, a little bit older than the initial population we tested, which were 5-month-olds. So there's no statistical difference between, reliable difference between the males and females at either age. They're just not really doing it. So in thinking about the data, you probably won't notice this because you're not as familiar with these kind of looking time studies as I am, but these looking times are really very low. I mean, 2 seconds on the part of these females, they're just not that interested in the stimuli, especially at that younger age, and that's really, really unusual. 3-month-olds are usually very, very interested in anything we have to throw at them. So I got to thinking, and then I just did a quick t-test to look at the differences in habituation looking times between the hand and the object. And this is across ages and across sexes, but by and large, they're looking a lot longer at this cube object here, on average about 140 seconds during habituation, and a little more than half of that looking at the hand during habituation. They're looking much, much less at the hand. Looking less, presumably learning about it less, perhaps not able to learn about its orientation because they're just not as interested in it, they're just not looking at it very long. So I'm not sure what this means for mental rotation. I'm not sure what this means for our hypothesis about differences between boys and girls and their sort of intrinsic preferences for mechanical or abstract stimuli versus social stimuli. I don't know. But it is very puzzling why this would be, and I don't know what the answer is yet.
Well, they spend a lot of time looking at their hands. They're fascinated with their hands at 3 months.
Absolutely.
And so there's a novelty effect there, which I think would account for most of the difference.
That's entirely possible. If that's true, you could still pull out some, there's still some hypotheses you could pursue in the existing data set, even though the looking is pretty low, which one hypothesis would be the kids who do look longer do have more time to look, or sorry, more time to learn, and they would be the ones to show the effect. But I looked at that hypothesis in the existing hand data, and I didn't find that. I also looked at that hypothesis in the object data, and I didn't find it there. Either. So I don't know. You're absolutely right, of course, that 3-month-olds certainly have discovered their hands. They spend a lot of time looking at their hands. They're just on the cusp, especially at 6 months. 6-month-olds are reaching. 3-month-olds have certainly discovered their hands, and they're on the cusp of being able to reach for things. And bad at things, so that might have a lot to do with it. It could be this is actually a really crummy choice of a stimulus to test mental rotation in. I don't know. Yeah?
It's also related to this question. They also probably have some understanding that hands kind of mirror image pairs, whereas that top thing is completely novel, so there's no prior belief that they can use that.
So there's nothing at stake here.
Right. There's
Yeah.
nothing to learn.
Right, nothing to learn, exactly. There's no reason to think that there's something special about a left hand or a right hand. That's entirely possible as well. Yeah. Yeah.
Are there differences in mean habituation trials between the hand and object?
The number of habituation trials? I don't know. It would be very easy to find out, and I didn't look at that. Once I discovered this, I thought, okay, I'm done, I'm just gonna go get the talk. So, yeah, I don't know. Would that matter beyond
Well,
this?
if they habituate faster, for instance, I mean, you could tell a story either way, I think, but if they habituate very fast, they could just be not really paying.
Well, they did habituate faster. They spent less time looking during habituation, they habituated
Okay.
faster. Yeah.
But did it take 12 trials or take 6 trials?
Well, actually, I did notice that a lot of the 6-month-olds took 12 trials to habituate, which is the maximum that we allot them. So I don't know what that means. So even though looking is lower, there were more trials. So those of you who are not infant sort of perception people and don't really care about the minutia of experimental design and everything, to those of us who are trying to eke out some little teeny pattern of meaningful data out of these kids who are otherwise drooling and pooping and everything, these things matter a lot to us. And I just don't know what the answer is. Yeah.
I don't know how it works, but given that they're not as interested in it, their overall looking time's lower, wouldn't it have to take longer given your criteria to habituate? Because of the sort of percentage drop, and you can drop more if you're really interested in something first.
That's a good point. Maybe, but not necessarily. That's why, like, babies who habituate after 12 trials, their accumulated looking during habituation still could be substantially less than a child who is very interested, but whose habituation curve, as you suggest, might be more precipitous, in its decline. But yeah, those are the things I haven't really been able to figure out yet. But anyway, these are all sort of relatively uninteresting, extraneous considerations. What we really want to know is the cognitive operation, and we're just a little bit too far away from that, probably because of the unfortunate choice of stimuli. But still, it's kind of interesting to think about. Okay, so one final study that I wanted to tell you about that we haven't started yet, so I'll just make this very brief. We are about to launch our first ERP study, and this is actually our daughter Veronica when she was 6 months old, with one of these sort of ERP nets on her head. And here's the study. It's a very, very simple study. We're just going to show pictures of objects for 1 second each, mechanical objects or social stimuli, or sort of distractors like this fractal image. So we have some social stimuli, this face, this hand, Elmo, this face, maybe the teddy bear is social. Mechanical objects might be this bicycle, this car, this clock, the telephone. I'm really not sure what the best way to characterize social stimuli, what's the best way to characterize mechanical stimuli, but we're going to find out. All we do is present these displays to infants and let them look and record their brain activity. And there's a number of different dependent variables that we've been talking about in my lab. Event-related potentials, gamma, which is a particular way of expressing EEG, power in the EEG spectrum, the electroencephalograph. And we even have the ability, although we don't really know how to do it yet, so maybe we don't have the ability, but we have the tools to look at cortical sources using EEG. In other words, we can actually come up with conclusions about the sources within the brain, not just at the surface of the scalp, about the particular cognitive perceptual operation that's going on. So these are the things we're talking about in my lab, and it would be very interesting to see if we could elicit sex differences in some of these outcomes. Okay, so here's the end of the talk. So I've already talked about all this. This is the same stuff we saw before. Yeah?
You say those are displayed for only 1 second?
Yeah. Yeah.
How many kids see them for infants? I mean,
Well, this is a very common method in infant ERP work. You sit the kid down and you just show picture after picture after picture after picture, and they have a very, very brief time to process. But in that 1 second, there's enough time to make a couple of eye movements and for some of that information to get in there. And I can tell you from lots of ERP studies have been done with faces, for example, even with very young infants, as young as say 3 and 4 months of age. And when babies look at faces, you can get ERP components that are dissociable in terms of different aspects of face processing. For example, upright versus upside down faces. So, you know, it's a very brief presentation, but you actually don't want them to spend a whole lot of time looking at it because you don't want them to get bored, you don't want them to make a lot of eye movements because that will gum up the ERP signal. Also, rapid presentation like this keeps them interested and hopefully gets more data. But, you know, we'll see. Okay, so these are the things I had to say before. And then here are some of the questions that remain. The big question for me is what the developmental mechanisms are, and I'm a long way from understanding that. I've already talked about this next question, are sex differences possibly a consequence of the kinds of stimuli that we use? And we want to know also about individual differences in hormone levels, preferences, or patterns of visual attention. So we're going to do some of these studies on the eye tracker to see if saccade patterns and other kinds of eye movement data might be related to mental rotation performance. And I'm a long way from this last question, and I'm not sure if we're in any position to contribute to it, but we might be able to, whether our developmental research and others can inform the mental imagery debate. So we'll see. And I'd like to end by thanking my colleagues, especially my buddy David Moore at Pitzer College, who got this whole thing going, and some of the folks at UCLA, and Casey Saska, who's at NYU, and my crack team in the lab and the funding agencies. And thanks to you for your attention. Thank you.